All right, hey there, Earth Science students. Today we're going to be doing our first video about plate tectonics. We're talking about continental drift theory. All right, so the theory of continental drift, it was proposed by this guy right here, Alfred Wegener, back in 1912, and he was one of the first people that thought that maybe our continents were not sitting in the same place all the time. So we call this theory continental drift. So he claimed that all the continents were at one point connected to form a supercontinent called Pangaea about 200 million years ago. So he wasn't just making this up. He had some evidence for his continental drift theory. The first is that certain continents seem to fit together like a jigsaw puzzle. So we can see here South America kind of fits in with Africa. The second piece of evidence was that he found the same fossils on different continents. And a lot of these fossils were things that were not able to swim or fly across the oceans that exist there now, like the ocean between South America and Africa, the Atlantic Ocean. He also found evidence of warm climate fossils in coal beds in cold environments such as Antarctica, suggesting that maybe they weren't always at the poles. He also found similar mountain ranges and mineral deposits found on separate continents. So we can see this here, similar mountain ranges in North America and Africa, and then similar rocks found between Greenland, the British Islands, and Scandinavia. The problem with this theory, though, is that he didn't have a how, right? He didn't know how the plates were moving. He just knew that there was a lot of information that was pointing to the fact that the plates may not have always been where they are presently. This is why we've developed a theory called a plate tectonic theory. So a tectonic plate is a section of the crust of the Earth and is moved by convection currents below the mantle. Here's a map in your reference table that shows you all of the major tectonic plates, what kind of boundaries that are between them, and what direction they're moving in. So you can see down here with our key, we can see what direction each of these plates is moving, and the transform, divergent, and convergent boundaries are all labeled down there. And we're going to get into what those are in a minute. So what's causing these plates to move? Well, that is convection currents within the mantle. So we've talked about convection before. We've talked about how gases or liquids, when we heat them up, become less dense and start to float. Now, the same thing is happening within the mantle. Now, the mantle is not purely a liquid. It's kind of like that taffy in between of liquid and a solid. But when you heat it up, it starts to become less dense and it starts to well up in the mantle. Then as it gets to gets close to the crust, it begins to cool down, become more dense, and begins to sink. Now, this pattern continues over and over again, and it pushes the continental plates either apart or starts pulling them towards each other. All right, are all of the continents moving in the same direction? No, in some cases, plates are moving away from each other and others are moving towards each other. And we're going to talk about what each of these different boundaries entails. So here, let's look at our different types of boundaries. First, we have convergent boundaries. So these are when plates are moving towards each other. So some of their identifying features. We're going to see mountains, deep sea trenches, volcanoes. Those are some things we can find at convergent boundaries. Now, depending on what types of crust we're dealing with, we're going to have different things showing up at our convergent boundaries. In the case of a continental convergence, like up here, we're going to have mountain building. And in case of oceanic and continental, we're going to have oceanic trenches and we're going to have volcanic arcs forming. All right, we also have divergent boundaries. So this is when plates are moving away from each other. And as they move away, that relieving of pressure causes volcanic activity, and that produces new crust in between. And at that spot, you end up getting these nice ridges. Transform boundaries. These are when plates are sliding past one another. So some of their identifying features are fault lines, like the San Andreas. It's a famous one. So you can see we've got two plates moving past one another. Not all crust is the same. So we got two different types of crust. We have oceanic crust, which is high density, thin, and it's made out of the mafic igneous rock basalt, and we find it under the ocean. Continental crust, on the other hand, low density, thick. It's made of the rock granite, which is a felsic igneous rock, and it rises above the oceans to create continents because it's thicker. So a subduction zone. This is a special kind of zone where we have a oceanic crust and a continental crust colliding with each other and in a convergent zone. And it creates this unique situation called a subduction zone. So what's happening in a subduction zone? We've got oceanic crust that's denser. It begins to go down underneath the continental crust. It plunges back into the mantle where it is recycled. As that happens, something occurs to the rock because seawater is introduced down there, and it changes the properties of the rock, allowing it to melt easier. That's where we get this right here, where we have material that is being melted, and as low density starts to rise up and produces a volcanic arc near our oceanic trench. So this is kind of the calling card of a subduction zone. You're going to see a trench and a volcanic arc. Those two things in the same spot mean you got a subduction zone, and you have oceanic continental convergence going on. All right, seafloor spreading. This is the process that creates new ocean crust where tectonic plates are separating. So it's a divergent plate boundary between two pieces of oceanic crust. So we can see right here, our ridge is going to be in the middle, and we've got our oceanic crust going one way and the other way. And we get our ridge right here where we have volcanic activity and new crust is being formed. As the tectonic plates pull apart, magma rises to the surface and erupts. Happen very slowly as the tectonic plates move apart. They're moving at about 1 centimeter apart at the mid-ocean ridge in the Atlantic between Europe and North America. So that's about how fast they're moving, 1 centimeter per year, which is not a whole lot, not very quick. So what's our evidence of this? So one piece of evidence is that as we get closer to the mid-ocean ridge, the rock is younger, and that pattern repeats itself on the other side of the ridge. So you can see this central spreading ridge is right here. We've got younger rock on right next to it, and then as we get further out, the rock gets older and older, and that pattern repeats itself on either side. So more evidence. So, all right, here's some more evidence. So iron-containing minerals point north when a rock containing iron starts to solidify. A lot of those iron-containing minerals are the first things to solidify in a rock, and they are pointing north. Throughout the Earth's history, though, poles have reversed several times. So that means that if our positive is at the North Pole and our negative is at the South Pole, that's flip-flopped several times throughout Earth's history, and that's kind of encoded into the rock. So the orientation of those iron-bearing minerals is going to change. And what scientists have noticed is that on either side of that ridge, that pattern repeats itself as it's moving further away from our mid-ocean ridge. So you can see right here, you're going to see a pattern that's going to repeat on either side of the mid-ocean ridge of the polarity of our iron-bearing minerals. And all right, that does it for this portion. Next time we're going to be talking about hotspot volcanoes.